I'm going to talk to you today about all-terrain autonomy for agriculture. And let me just get started with showing you 3 projects I've worked on in the past 10 years. It's really been like a special experience to build a autonomous truck. So think semi-truck, 10 tons of metal driving over the highway at 60 kilometers per hour or 60 miles per hour here in America. Without a driver in the seat. So this is the kinds of things we've been doing in the early days of autonomous driving. And you better make sure that your planner and control stack work for that truck scenario. Then a little bit more relaxed, maybe self-driving parking and autonomous industrial robots. But maybe one thing you might notice is these 2 images, they're actually, they're not pictures, they're not photos. They have come out of a simulation. And so this was a crucial aspect of these 2 projects, that we trained the robots in simulation and we tested them in simulation to basically predict how we're going to perform in reality. And I'm going to talk a little bit more about that next. So with all of that being done, I said, what do I do today? And maybe you've seen that little joke. So apparently I've become senior now after working on this stuff for a long time, because this is how my working place looks today. It's a farm. And yeah, we also have an office, so don't worry. So we actually don't program on the farm because we don't even have internet or anything on the farm. But these are the problems we're trying to solve today at Farm NG. And I think for me, it's really important to think about, where does the food we're eating come from? Is it grown sustainably? Is it healthy? Does it still have taste to it? Or is it just, these flavorless strawberries you sometimes eat? It just tastes like water. And is it farmed under humane conditions? Because you have to imagine, if you buy a box of strawberries, or like one of these boxes of blueberries, there's maybe like 200 blueberries in one of these boxes. And every one of these blueberries, strawberries is picked by a person manually from the bush. So it's hugely labor intensive, this kind of work. And there's a labor shortage in that market. No one wants to do this work anymore. And so we're trying to find solutions for that. So let me show you a little video for what we're building. We're building the Amiga. It's an electric modular platform, which is suitable for a variety of farming tasks. And when I say farming, you really have to think about specialty crops. So don't think about wheat and soy and corn. I think we heard some talks today about that, where you come with these giant machines, with these giant boom widths. But we're building a small factor, which is suitable, a small platform, which is suitable for farming in greenhouses, farming on smaller fields, farming for smaller growers, and really growing crops like berries, also maybe grapes and orchards, carrot and salad. So everything where there's like a huge labor factor involved. And a crucial component is that this robot, of course, you don't want to drive this yourself. But what the vision we want to enable is that you have multiple of those robots and they drive autonomously on the field. And the key component here really is it's electric, so no more diesel, no more CO2 emissions. And it's also much cheaper to do it electric, by the way. You wouldn't believe how much fuel you have to pay as a farmer, how much you have to pay for fuel as a farmer. It's a modular platform, so it's extended for different use cases, and the goal is to make it fully autonomous. So let's talk about the autonomy part. How do we make it autonomous? And I just wanted to show you a little slice of the data we're looking at here. So this is from our strawberry data set. So one of these applications we're looking at. And you can see, most of the time, like some of these pictures here, you look basically at a furrow. So they're like raised beds, and then you have these pathways the robot needs to drive through. So most of the time you look at the forest. So it reminded me always a little bit of highway driving. Highway driving basically, I don't know, you ever drove through Nevada or Arizona, nothing happens for an hour. You basically, like we used to joke, just drive straight is all the autonomy stack needs to do. But then, suddenly, you have certain scenarios where there's a lot of activity. People are involved, or like equipment, there's some objects blocking, And of course, the autonomy stack needs to handle those. So this is really the target for us. So let's have a look at a little bit the philosophy we like following at FarmNG. And our stack is separated in three pieces. It's the perception part, machine learning, deep learning. But then we don't use reinforcement learning. We have basically numeric optimization, motion planner, and behavior planner. And then the last part is even separate. I cite this even separately is path following and trajectory following, path following, trajectory planning, and the control part. And the separation basically has the reasons because the requirements are different. And also the methods and how we verify that it's working correctly are different. So for example, on the right side, for the control trajectory planning part, the biggest requirement is actually the safety. Do we keep our speed limits? Do we drive in a safe way? Do we not suddenly make big turns? Do we communicate correctly with some other mechanisms like beepers or stack lights? And we really can only finally test that in live test, but we also do some of the tests then in simulation. However, in comparison, on the perception side, for me, the requirement really comes from our ML data pipeline. Let's get the robots out there, let's record that data, let's observe what's happening in the real world, and feed that back, and then kind of form this body of scenarios we need to solve. And I don't think there's really a replacement for that, right? You need to do this exploration part. You need to go out there and collect and collect and collect and collect. You need to collect smartly so that you're not only driving on these Nevada highways forever, but you're really finding these interesting scenarios also. But the verification, for example, looks differently because let's say if you don't have a photorealistic simulator, you need to do this on log files. And photorealistic simulators, we heard a little bit about in the panel, they're expensive. The assets are expensive. It's really hard to set this up properly. So we have these different methods on how we verify that. And I think for me, that's very important to not look for this one strategy to do it all, but separate it up. So just two quick slides here on the perception stack itself and how it works a little bit inside. So we have multiple cameras mounted around the robot, and they're all fused together into a bird's eye view grid map. So it's kind of like a popular technology these days, looked also in autonomous driving, used in autonomous driving quite a lot. We kind of have the luxury is that our grid maps, for us, the robot is driving not as far as an autonomous vehicle or an autonomous truck. So the basically area of interest we need to cover is a little bit smaller around the robot, right? Because it moves a little bit slower. So that especially is helpful for these kind of bird's eye view approaches. And then what we integrate into these bird's eye view approaches, so we fuse all the data we have into that bird's eye view, is basically the height profile of the terrain. Because it's again that highway driving problem. Most of the ground is flat, even on a farm, but then you have these ditches and suddenly there's like a pothole, so to say, for lack of a better word, where there's like some water in a, and then suddenly the robot like dips down into that hole and maybe loses contact with one wheel, so it can get really ugly. So we want a height profile, detailed height profile of the terrain, and then of course we want to know about people moving around the robot, and the general basic semantic meaning of what's happening around it. I can't talk too much about the details here, but I still wanted to show one of these diagrams, working at NVIDIA for a long time. So basically, we have an encoder, this should say decoder here on the right side. So we have an encoder into this fused bird's eye view latent space. And so it's really, so to say, what people also call, in a way, it's early fusion. So we take all our data and we put it into the network and we fuse it basically early. We don't have a bunch of algorithms and then fuse them afterwards to get to these results, to the bird's eye view. One more thing which is really important for us and also for me personally is the simulation. So how do we use simulation? And we actually, as mentioned earlier a little bit, we don't have that one big simulator. We try to look a little bit for it, Maybe we use Gazebo, but then we don't have rendering in Gazebo. Maybe we use only log replay, but then how do we test our planner, right? So we actually have multiple different tools and verification methods Because for us, what is important is how do we actually use that simulation stack? And we heard a lot about, we can train the neural networks in simulation. But what's important for us right now is basically how can we predict the performance of our stack? So we're building the stack, we're training the stack. How can we predict that it works in reality? Because what you have to imagine is that live tests, what people started out to do, of course, they have very high relevance. That's ultimately what you need to show, that it works in a live test. But they're very slow and very expensive. And I think this key strategy really is to maximize that iteration speed, minimize the time it takes to do one iteration loop. And so this is why we use like a variety of tools. We have a tool built in-house, kind of called Flat Farm Sim. Everything is flat, no bumpy terrain, nothing. Perception is really more like very crudely simulated. But we can use that tool to test a lot of our planner stack and our control stack, and it's really fast. It's really easy to optimize. And so we know for that, you remember maybe for that third part of our stack, we can already have very good prediction that this is working and being able to handle all these scenarios. Then we use Mujoko, a simulation based on Mujoko, to bring that 3D aspect into it, and also a little bit these ground interactions into it. But I do have to say there's still a lot of work to do in terms of accurate tire ground physics. And although our platform is not, in the technical sense, touching something, it doesn't have fingers or hands, but it is touching the ground with its wheels. And that interaction is non-trivial at all. And it's a little bit neglected, I have a feeling. But still, this gives us a full 3D form. And of course, we have the log replay, and then ultimately the live test. We started also using NVIDIA Omniverse for the photorealistic simulation to basically also bring that into the loop of our training pipeline. So let's have a look then, if everything goes well, how this looks like in reality. So this is an application we're looking at right now in the strawberry field. And for me, what is the criteria? Oops, sorry. What is the criteria of when does it work? How do I know that it works? Of course, we can have all these, statistics and incidence reports in it. But I also always feel as if it's extremely boring and unexciting, that's actually when it works well. We did this experiment and people came to see, does it work, does it not work? And everyone was quite disappointed because nothing else happened than the robot just driving up and down these furrows forever. So a very boring experience in that sense. But of course, for the engineers who worked at it, we were quite happy that the whole pipeline we exercised here works well. So that's it. So thank you very much for your attention. If you want to learn more about farming, farming.com is our website. That's my email address. So thank you very much.